So now we solve for the optimal behavior in all of these building blocks. The first here is the profit maximization of intermediate goods producers. Their profits are given by the price that they can charge for their intermediates, so PL for the producers of intermediates that are produced with low-skilled workers and machines suited to low-skilled workers. And here we have the profits of the firms that produce the intermediates with high-skilled workers and machines suited for high-skilled workers. So the first term here is revenue, the price I can charge multiplied by my amount of output that I sell. And then I have to subtract the wage bill. And here I have to subtract outlays for machines. Then I get the profits. And the same holds true for the intermediate goods producers that produce with high-skilled workers. Now machines fully depreciate after use, so therefore it's a static optimization problem. I don't have to take care of the scrapping value or something like that of the machines later on. Then profit maximization would be that I take the derivative of this function with respect to the two inputs in production that I can choose. And here we have the solutions for the inputs of the machines, because that's the demand function that I need in the sector, in the machine producing sector, as a side constraint for the profit maximization problem of the machine sector. So here I have the expressions that I get when I take the derivative of these profits with respect to the machine inputs XL and XH, and then reformulating yields these demand functions for the machines of type L and the machines of type H, which are increasing in the overall price that I can charge for my own output. That's clear, because if I can charge higher prices, I would also increase the demand for machines because I want to wrap up production. And then they decrease in the prices for the corresponding machines that I have to pay. That's also clear, because if the price of the machine that I need in my production is higher, I would say ceteris paribus produce less. And then output or demand for the machine would increase in the production factor that I use intensively in terms of labor. So for the XL firms, it's increasing in L, and for the XH firms, it's increasing in H. And that's also clear. If there are more workers around that I can use in my production, I would say ceteris paribus increase the demand also for machines with which I can then produce using these workers. Now, using the results that we just had, we can also solve the profit maximization problem of the monopolistic machines producers, which leads to markup pricing because of market power, basically. So now the profits of the machine producers would be PL of nu T for the producers of machines used by low-skilled workers, and it would be pi HT for the other firms. So that's analogous to what we have here. That's equal to the price that I can charge for my machine multiplied by the amount of machines I produce as before, and I have to subtract the costs of production, which is the marginal input requirement of capital multiplied by the number of machines I produce. Now I can use the demand functions for low-skilled intensive machines and high-skilled intensive machines from the previous slide, actually here in the profit maximization problem, to substitute out for the prices actually that I can charge. And that's just reformulating these expressions, isolating PXL and PXH there, and plugging them into the profit maximization problem. And what we would then get carrying out profit maximization, so taking the derivative of the profit function with respect to output, would then be prices PLX and PHX that would be equal to 1. And that's a markup over marginal cost, because the marginal cost here was defined as 1 minus beta, and that's obviously smaller than 1. And therefore, if we have prices PLX and PHX equal to 1, then this would mean that we have a markup over marginal cost in this sector. And then we can substitute this result into what we had here. So just substitute out for the prices PLX and PHX, and then we get these demand functions for type L machines and type H machines here from the intermediate goods sector. Now we've seen a property that is also very familiar in this literature, that the quantities do not depend on the machine index, they only depend on the index of the sector that is served. But since they do not depend on the machine index, we have symmetry in these producers. So therefore profits are also independent of machine variety, and we get, if we solve that the profits are equal to this expression. So we plug it in, everything that we had so far, and if we solve it, then in the end what we would find out is that we have xf nu t here minus 1 minus beta xf nu t. So if we solve that, what remains is beta xf nu t, and that can then be used for the determination of profits. If we put it together with the results from the previous slide here, then we get these expressions for profits of the producers of machines for the low-skilled workers and producers of the machines for the high-skilled workers. And next, of course, we can then use these instantaneous profits to determine the value of monopolists and the value of the patents in the economy, of course. Next, we can combine the production functions that we had so far for intermediate goods of type L and type H with the demand for machines, equation 6, and this would yield output of intermediates L and intermediates H as the functions as they are here, depending on the stock of patents in the two for the two types of machines, and the price actually of these intermediates, and also of course the supply of workers that are low skilled and of workers that are high skilled, and that's needed later on. Now we can compute the marginal value products of the intermediates in final goods production, so of intermediate YL and intermediate YH. And this is just done by taking the derivative of the final goods production function with respect to the production factor under consideration. If we take here the derivative with respect to YL first, then from the aggregate production function, we get the exponent down due to the chain rule. The exponent is epsilon over epsilon minus 1. And the exponent itself is reduced by minus 1, which means that we subtract from the numerator in the exponent epsilon minus 1 actually, and what remains is then 1 over epsilon minus 1 in the exponent here. Then this part first here remains unchanged within square brackets, which is the same term as in the aggregate production function, because of the chain rule. And then we have to take the inner derivative with respect to YL. So this term drops out, it doesn't contain YL. And from this term, epsilon minus 1 over epsilon comes down from the exponent, and the exponent is reduced by minus 1, which in this case is subtracting epsilon from the numerator of the exponent, and we get minus 1 over epsilon. And the inner derivative here is just 1. So this is the expression, the marginal value product of intermediate YL, and it's also the marginal product because the final good, the price of the final good was normalized to 1, and the final good therefore was the numeraire. And a similar expression holds true for the marginal value product of the intermediate YH. And then we see epsilon over epsilon minus 1 and epsilon minus 1 over epsilon cancels out, and we arrive at these expressions here. Now we can put together what we know from here. So we take the ratio of the marginal products of the two intermediates, and then actually a lot drops out because we've seen here that this term here is the same for both, so it drops out, and what remains is actually on this side here. So we would have YH over YL to the power of minus 1 over epsilon, and we have gamma here in front, which is the ratio of the two gammas. Then we can plug in what we derived 2 slides before, the YL and YHs from 8 and 9, into this expression. Then we get this expression here. Now this can be further simplified because PHT over PLT is already known from the previous slide to be the ratio of marginal products. So that's the same as PT, which is on the left-hand side. So we then have PT here as well. And we have it to the power of beta minus 1 divided by epsilon times beta when we do all these simplifications here. And here we would still have NH over NL times H over L to the power of minus 1 over epsilon. Then we can isolate PT on the left-hand side. Then we get PT to the power of cluster of parameters, basically. And on the right-hand side, we still have this expression here multiplied by gamma. And then finally, we can bring this exponent to the right-hand side to have PT isolated, so the ratio of the marginal products or the ratio of the prices of the intermediates in final goods production, which is then a function of parameters here, and the ratio of the supply of high-skilled workers multiplied with the stock of technologies that are suited to high-skilled workers divided by the number of low-skilled workers multiplied by the stock of technologies suited to low-skilled workers, and that's to the power of minus beta over sigma. And sigma here is basically epsilon beta minus beta plus 1, so that's the numerator of the exponent here, and one can simplify that to 1 plus epsilon minus 1 times beta. And that's now the derived elasticity of substitution between the two production factors YH and YL after considering that they are produced with H and L and with the machines and so on and so forth. So that would then be the overall derived elasticity of substitution that depends crucially on the elasticity of substitution in the final goods production function epsilon. Then in the next step, we can calculate the marginal value products of the two production factors H and L, depending on what we already know from previous calculations. We use here the expressions 8 and 9, because if we take the derivative of these expressions here with respect to L and H, we get the marginal value products of these two production factors. So that's exactly what we do here, and as a result, we would have these expressions. Now we can use these expressions to calculate the ratio of the marginal value products of high-skilled workers divided by low-skilled workers, which would actually be the ratio of the compensation of these two production factors. So that's basically then the skill premium in the end that we denote here by omega. It's omega H divided by omega L, the ratio of the two marginal value products. So we take the ratio, this term here drops out again, and what we get from here is NL and NH, where we have to divide then. And here we summarize the two terms here, PLT to the power of 1 minus beta over beta times PLT here would be PL to the power of 1 over beta, and here PH to the power of 1 over beta, and what we get is then this expression here. Now we see that this is again PT actually from the previous derivations, so we can plug in the result for PT in this expression. And then we can simplify further, and then we would get in the end the skill premium as a function of parameters gamma to the power of epsilon divided by sigma, so of the elasticity of substitution, but that's not that important here. What is important is that it's a function of the fraction of the stocks of patents for high-skilled machines and patents for low-skilled machines, and the supply of high-skilled and low-skilled workers. And now we can already see where the whole thing converges to actually, because we have here the skill premium as a function of technology on the one hand and relative skill supply on the other. And that's very close to the function that we had in the beginning when we discussed the intuition behind the model. And we will now solve for the equilibrium relation between NH and NL, as determined again, as we will see, by the ratio H over L. And after we have done all that, we can then compute how the skill premium changes overall if H over L changes, and this has then another knock-on effect on NH over NL. Now what we need to solve the model for the equilibrium skill premium is the research and development sector, because in the research and development sector, this ratio is determined endogenously. And what we have in the research and development sector are the free entry conditions for research and development firms. that state actually that if I have a certain amount of resources to invest in research and development, I would only invest it in the corresponding research and development if the rate of return is at least as high as if I invested in other activities in the economy, either for producing machines or for the other R&D activity, so tilted towards the high-skilled workers, for example. So here what we have is the productivity of resources in producing patents for low-skilled machines multiplied by the value of these patents. Now, if this is smaller than 1, strictly smaller than 1, I could increase my rate of return of investment by investing, say, in machine production instead of research. So I will only invest in research for this type of machine patent if the product of eta L and VL is equal to 1. And a similar argument holds true with respect to investment in the production of patents used for high-skilled suitable machines. So that's this expression here. So in equilibrium, we will have that the two expressions here would be equal to 1 because we have investment in all of these things, so machine production and R&D of both types. But what then happens in the background is if there is a shift in relative supply of workers, H over L, then this induces also a shift in the relative profitability of research and development. And in our case, as we will see, we will have equilibrium bias towards high-skilled workers. If the relative skill supply of high-skilled workers increases, we will see that the profitability of the high-skilled research and development sector would increase ceteris paribus. So resources would move out of this research and development sector and into the other research and development sector, implying that the fraction of patents along the balanced growth path of this research sector versus this research sector would go down, basically. Now, along the balanced growth path, we have that consumption growth stays constant at rate G star, and therefore also the prices stay constant, basically. And in the research arbitrage equation, we have that there are no valuation gains of the different shares, and therefore no valuation gains, no changes in the value of the patents. That would imply in equation 5 that the interest rate is also constant, and we can derive the value of the patents as the profits divided by the interest rate in equilibrium R star. And this holds again for both types of patents that we have in the economy, the one that are suited for the machines for low-skilled workers and the one for the machines for high-skilled workers, basically. Now we can divide the two expressions from the previous slide to get the relative value of patents for the patents that are used by high-skilled workers and the patents used by low-skilled workers here. So if we divide the two, we see R star drops out, beta drops out, and the only two things that remain in the expression are PH over PL to the power of 1 over beta and H over L. And these are exactly the two forces that we talked about when we talked about the intuition of the model, namely the price effect and the market size effect. So if the relative price of type H intermediates goes up, then this would imply that also the relative price of type H patents goes up. And a similar result holds true if the relative skill supply of H over L goes up, then also the ratio of the value of patents would go up here. So the market size effect and the price effect. However, this is as of yet incomplete because the prices are endogenously depending on the fraction H over L, which is also obvious from inspection of equation 10 here, where we see that the prices here are endogenous and depend on H over L. So that's the next that we have to solve for. Now to this end, we can plug in the ratio of prices PT from equation 10 into the ratio of the value of patents that we had on the previous slide. And then we see we get an expression in square brackets that depends on H over L. We also have H over L outside here. And if we summarize the two terms, we would get this expression here, where the ratio of the value of patents depends on the stock of patents, the ratio of the stock of patents, and the relative skill supply to the power of sigma minus 1 over sigma. And now the elasticity of substitution, sigma, regulates whether the price effect or the market size effect dominates, and we note that sigma smaller or greater than 1 is equivalent to epsilon greater or equal than 1. So basically the elasticity of substitution between the two production factors, the derived elasticity of substitution, is determined by the elasticity of substitution of the two intermediates in the production function. And the two production factors H and L are gross substitutes if the two intermediate goods are gross substitutes. And now what we see here is that an increase in H over L would imply an increase of VH over VL if the elasticity of substitution is greater than 1. So if the two production factors are gross substitutes, which they are empirically, because high-skilled and low-skilled workers are typically substitutes on the labor market. However, there is still one aspect that is endogenous in the previous expression, and that's the ratio of the stock of patents. But here, fortunately, we can use the expressions that we had in the innovation sector, where we know that in equilibrium along the balanced growth path, it must hold that the product of the productivity of resources in the two types of innovation sectors multiplied by the value of the two patents has to be equal to each other, because otherwise there would not be investment in one of the two, basically. So that follows from the free entry condition. Now we can use that basically to isolate VH over VL on one of the sides here, and combining the equation 12 here and equation 13, where we would then get eta L over eta H is actually VL over VH. Now VL over VH can be plugged in from equation 12, basically, and then we would get this expression that we have here. And now in this expression, we see that NH over NL is still present, but we can isolate it on the left-hand side. So we bring it to the left-hand side, eta L over eta H, we bring it to the right-hand side, and we can compute for the equilibrium ratio of the stock of patents that are suited to high-skilled workers divided by the stock of patents used by the low-skilled workers, NH over NL star, which is this expression here, which is just the simplification of the expression that we have above here, and eta is now eta H over eta L. And this expression can then be plugged into this expression here, such that we can next solve really for the equilibrium skill premium that is only determined by exogenous parameters anymore. To this end, we can now combine equation 14 from the previous slide with equation 11, which we had here. So we plug in 14 into 11 to compute then finally the equilibrium skill premium that only depends on exogenous parameters. So we have this expression, we plug it in, and then we get this expression here, which can be simplified easily because we have a gamma here. So in the end, we would have gamma to the power of epsilon outside of the brackets. We have H over L in square brackets and H over L here. So if we summarize everything, then we will get H over L to the power of sigma minus 2. And this is the central result that we aimed for, and which we can now use to explain the initial puzzling finding that the skill premium goes up when the ratio of high-skilled workers goes up. Now, the interesting thing to note is that whenever sigma is not equal to 1, there is always a weak equilibrium bias, in the sense that an increase in H over L always induces H-biased technological change. And that can be seen, for example, in equation 14, that for sigma is greater than 1, an increase in NH star over NL star is biased towards H, while for sigma smaller than 1, a decrease in NH star over NL star is biased towards H. However, this weak equilibrium bias that is always present in the model, except for the Cobb-Douglas case, but that's the uninteresting case that we do not consider in this chapter, this is not yet sufficient to guarantee an upward sloping labor demand curve, basically, or that the skill premium increases if H over L arises. For this, we need a strong equilibrium bias, and a strong equilibrium bias would prevail if sigma is greater than 2, meaning that the two production factors H and L are rather good substitutes. And we see this here immediately. If sigma is greater than 2, then an increase in H over L would lead to an increase in omega, which is the skill premium, the wages of high-skilled workers divided by the wages of low-skilled workers. So this goes up if sigma is greater than 2, but it goes down if sigma is smaller than 2, even if there is weak equilibrium bias, because then it's just not strong enough to overturn the results. So in terms of the figure that we had at the beginning, where we had the relative skill supply on the horizontal axis and the skill premium on the vertical axis, we would be in the initial equilibrium, have H over L, that's relative skill supply, and the downward sloping labor demand curve. Now for an increase in the relative skill supply, we would end up ceteris paribus at a skill premium omega H over omega L that is lower than the initial skill premium, which would be the case if there is no reaction in technological progress. However, there is a reaction in the skill bias technological change model, and there is always at least weak equilibrium bias. So we would always have a situation where we do not end up in this equilibrium after all the endogenous technological adjustments take place, but we would end up in an equilibrium with a higher skill premium than this ceteris paribus skill premium. So in this case, as it is drawn here, we would be with the endogenous technology curve 1, and we would end up with a skill premium WH over WL prime 1. So we would end up with a higher skill premium than in this equilibrium. However, only in case of a strong equilibrium bias would the long run labor demand curve be upward sloping. So that would be endogenous technology 2 here, which would be the case for a strong induced technological progress. It is biased strongly in favor of high-skilled workers, and for a high elasticity of substitution. Then we would get this result here, and the skill premium would actually be higher than the initial skill premium before we had the increase in the relative skill supply. And how would the dynamics look like for these adjustments? Here, in case of weak equilibrium bias, we would have an increase in the skill supply, and first the wages would move down to the ceteris paribus wages, but then over time we would have this skill bias technological progress, and the skill premium would again increase slightly. So the wages would go down, but then up, but they would still be lower than in the initial equilibrium in the long run. However, for the strong equilibrium bias, we would have a decrease in the wages again initially, but then in the long run, the wages would end up even higher than in the initial equilibrium, which would be the case for the endogenous technology curve 2. So in this case, we would have the situation of a strong equilibrium bias, and that prevails if the elasticity of substitution is greater than 2. Now, what can we explain? So what we've seen is that there was a rapid increase in the number of skilled workers in the second half of the 20th century. So that's basically by this graph here, we see that the number of skilled workers relative to unskilled workers has increased. So it increased both for men and women. So we see here the fraction of women with a high school degree and the fraction of men with a high school degree both tended upwards. Now, the model predicts that there is an initial phase of declining or stagnating relative wages because technologies need a certain time to be invented and technological progress needs some time to adjust. So that's what we've seen here. We have an initial decline and only later on an increase. Now, that's what we see here to some extent. So during the 70s, initially, the wages stagnated or even went down. So the skill premium basically even went down. And only then, in the 1980s, there was quite a rapid rise, actually. So this prediction of the model would be borne out by the data. However, the model can only predict the data or explain the data if the elasticity of substitution between the two production factors, low-skilled and high-skilled workers, is greater than 2. If it is smaller than 2, then actually the reverse holds true. Now, what can we say about the elasticity of substitution between low-skilled and high-skilled workers? Now, empirical estimates suggest that sigma is between 1.4 and 2. Now, in this case, the model would not be able to predict the findings that we see in the data, because for this elasticity of substitution between low-skilled and high-skilled workers, the model would actually only predict a weak equilibrium bias. However, one can write down a model extension where research and development is not given by the lab equipment approach, but by the standard intertemporal knowledge spillovers approach that Roma also follows in his paper, so where scientists produce research and development. And then one has to assume intertemporal knowledge spillovers, and these knowledge spillovers could be biased also in favor of one of the two types of research. So they are denoted by delta. Now, delta measures the extent to which knowledge spillovers are biased in favor of the corresponding type of innovation. If delta is 0, then actually an innovation, irrespective of whether it occurs in the H or L sector, would lead to an equiproportional increase in the productivity of researchers in both sectors. So then there would not be a bias in the intertemporal knowledge spillovers in the favor of one sector. If delta, by contrast, were equal to 1, then an innovation in the H sector would only lead to an increase in the productivity of researchers in the H sector in the future, and not to an increase in productivity of the researchers working in the L sector. So that would be the other extreme. Now, it's rather clear that the truth would be somewhere in between. So typically delta would not be equal to 0, but also not be equal to 1. But it's one can imagine that it differs to some extent from 0, so that the new condition under which the model would predict a strong equilibrium bias is then that sigma is greater than 2 minus delta. And if delta was, for example, 0.5, then it's quite likely actually that in reality the conditions are met for the model to imply a strong equilibrium bias, and then the model would be consistent with what we observed in the data. So that's the skill bias technological change model under certain circumstances. For the elasticity of substitution between low skilled and high skilled workers, it can predict an increase in the skill premium as relative skill supply increases.